And so today we're going to start talking about phase diagrams. This is this next section of the course. And so phase diagrams are exactly what they sound like, all the different phases of matter. So you're going to have solid, liquid, and gas. Those are the main phases that we'll deal with. Then we get into mixtures. So liquid vapor equilibrium and binary mixtures of liquids. So distillation, when we're separating liquids, we'll learn about distillation using phase diagrams. And then we'll get into solid phase diagrams. So different solid to solid transitions. And that's where it really gets interesting. I have an email from a student who graduated 4 or 5 years ago, and she said, you never know when you're going to run into this stuff. So she went to graduate school, and then she got a job, bounced around, and now she's working for a concrete company. And she's doing solid phase transitions. And she says, all of those phase diagrams that we talked about in PChem, I'm using on a daily basis. And she had no idea when she's sitting in here. I think she was interested in biochemistry and was working for Petrokovics, and now she makes concrete. So you never know. So I would just say it's all enjoyable and useful. That's why I love it. So let's dive in. This is just review. There's several slides in here that are just put in here for review, so you know you have them in a nice clean place, like the definition of bar and atmosphere, and then the difference between molar volumes. You might have memorized from freshman chemistry the volume of 1 mole of gas is 22.4 liters, but that's 1 mole at STP, so at ice water temperature at 0 C and at 1 atmosphere. So that's standard temperature and pressure, but a lot of these other calculations use SATP, standard ambient temperature and pressure, so it's room temperature and 1 bar. So that's different pressure and a different temperature. So I would say don't memorize molar volume, just calculate it. Okay, memorize the standard ambient temperature and pressure and standard temperature and pressure. And again, these are going to be posted in an updated form on the notes. Okay. This is a review slide, Dalton's law of partial pressures. Do you remember this? You just take all the individual partial pressures, add them together to get the total pressure. We do this a lot in mixtures because we have the partial pressure of component A plus the partial pressure of component B gives you the total pressure. So if you have a 50-50 mixture of an ideal solution, then the pressure of, say, acetone would be 50% of the pressure if it was pure acetone. And the pressure of chloroform would be 50% of the pure chloroform pressure. Add that together, you get the total pressure. But acetone and chloroform have different saturation pressures. If it was the totally acetone, it would have its saturation vapor pressure. And if it was totally chloroform, it would have its saturation vapor pressure. So Dalton's law of partial pressures, you just add those together. Then we'll see that there's a lot of violations of Dalton's law. Or of Raoult's law. When you take this Dalton's law, you end up with Raoult's law, that the pressure is equal to the mole fraction times the pure vapor pressure of that substance. And there'll be violations of Raoult's law when we get to those mixtures. So this is just a review slide showing you that pressures are additive. Let's talk about ideal gases. So an ideal gas is actually a very restrictive definition. The particle that we're calling the ideal gas has no volume. So it doesn't have any extent. It just is a point mass in space. So that's pretty restrictive. Nothing can actually collide with that particle until they try to occupy the exact same coordinates. And then when they do try to occupy the exact same coordinates, there's an infinite repulsion. So they're hard surfaces. But there's really no volume to that surface. They're just point masses, and when they do collide, if they do try to occupy the same coordinate, then it's infinitely hard, which means all the energy they bring in, it's conserved, it goes out. So there's no loss of energy in a collision. They're perfectly elastic collisions. We know that that's an ideal case, not a real case. Real molecules have volume, the volume of the electron cloud. Okay, a good estimate of that would be the 95% isodensity surface. So you have 95% of that electron cloud contained in that surface. That would be a good estimate for the volume of a molecule. And they're soft. If they get close enough, the electron cloud starts oscillating in concert and there's a slight attraction. So that's an induced dipole attraction or London dispersion force, which brings those those gas molecules together because of it's almost like a communication between the electron clouds. They start oscillating in concert with each other, and they generate a van der Waals attraction. But if they get too close, then the electrons in those clouds are repelling each other, and you see that the nuclei see each other. And so the nuclei start to repel. If you get too close, the electron cloud can move, but the nucleus really can't. And so the particles just get too close for their nuclei to be comfortable, if you will, and then they repel. But that's a much softer collision. You have some attractive force as the electron cloud starts to interact, and then you have this repulsive force of the nuclei. And the molecules can turn if they're not monatomic, and so then you've got a soft collision. You can think about it as a collision event comes into play, that the energy of the two colliding molecules drops down and rolls uphill and stops and then rolls back down. So you can just kind of think of this slope as the separation distance between the molecules. You can plot this potential energy curve, and you can see as they collide, if they don't have enough energy, or if there's a third body that takes away some of that kinetic energy, then they might get stuck here. And they would be in an attractive dominant area, and they would stick. And so that's why whenever you have nucleation centers or walls in a gas and they cool them down, condensation happens where the third body is. So you've got a molecule that's kind of stuck to the surface, and a third one hits it, or a second molecule hits the first molecule, but they're stuck to the surface. Some of that kinetic energy can go into the wall, and now they're stuck to each other. And so you can have condensation on third bodies very easily because that kinetic energy is lost. So they come in, they would go up here with the collision, and the energy would be here, and then they would dissociate again. But if this excess kinetic energy is taken away by the third body, then you get condensation. So today we're going to really talk about condensation and the phase diagram associated with condensation. These are the isotherms for an ideal gas, and you have no condensation in an ideal gas. And so what if you did have condensation? What would it look like? So let's come in on, let's say, this isotherm right here, and we say right here we hit the vapor pressure of the liquid. So what is the vapor pressure of a liquid? It's that pressure of the gas above the liquid. And it's a function of temperature. And these are isotherms. So we're staying at the same temperature and then just decreasing the volume. So once we hit that vapor pressure of the liquid, liquid starts to form. And as we decrease the volume, all we're doing is just condensing the liquid. Eventually, the volume gets to the volume of those many moles of liquid. So you can't compress it any further very easily because all the gas is condensed, and now you've got a container fully filled with liquid. And now you're just pushing on the liquid. And what does the pressure do in that case? It shoots up. So now you're pushing on the pressure on the liquid. And so you have the gas, which I'll call vapor, V, vapor. Then you have V, vapor plus liquid, and then you have liquid only. So that's what condensation would look like. And you see, the ideal gas has none of that in it. Okay. Ideal gas, you just have these nice isotherms. So when we're talking about isothermal expansion, we were using PV plots for the Carnot cycle and for the Stirling cycle and all these different kinds of cycles. But we were way out here to the right because we wanted our permanent gases to be, useful. So we were far to the right using isotherms and adiabats. Now we're decreasing the volume and we're compressing our gas too far, and we're starting to see liquid form. And so what we drew by hand, don't worry about it. It's right here on the CO2, which we're going to get to. So looking at ideal and real equations of state, the ideal equation of state is the ideal gas law. The real equation of state is going to be something that's empirical, and we're going to have different zones. We're going to have an equation of state for the gas region. We're going to have a vapor-liquid equilibrium equation of state, and then we're going to have a liquid equation of state, and then solid-liquid where it's melting or freezing, and then we're going to have a solid equation of state. So there'll be different domains for these equations. And what I mean by state is you give it the state variables, pressure, temperature, volume, and number of moles, and then this will tell you the energy associated with that arrangement. And so just looking at this, you've got these different isotherms. If I were to give you any one of these points, and this is going to be how I will test you on this, is I will give you a letter, like I'll show you this diagram on the right, and I'll ask you, where is, this point A? Is that a solid, liquid, or gas? Or some mixture of those. And so this point A right here is beyond this condensation region. So that's going to be a gas only. B, also a gas. But at C, we start to see condensation. And so we have vapor and liquid in equilibrium at C. We have vapor and liquid at equilibrium in D. We have vapor and liquid at equilibrium in E. At E, it's almost all liquid. At C, it's almost all gas. At D, it's about a 50-50 mole ratio of liquid and gas. And then F is all liquid. Notice this point right here. This is a special point. Can anybody guess what that is? No, it's not a triple point. Good try though. We'll get to triple points with a different phase diagram where it's a little more obvious what the triple point is. What other kinds of critical? I just said it. I was going to say, what other kinds of critical points on these curves have you seen? Well, it's called the critical point. Okay. I was trying to use it mathematically, like important points, but this actually is called the critical point. Okay, and so this is where above the critical point, you no longer have condensation. Okay. And so all your permanent gases at room temperature, like hydrogen and oxygen and nitrogen, we're way above their critical points. You're not going to get nitrogen to condense at room temperature. You say, but wait, I've seen liquid nitrogen. Yeah, it's at 77 Kelvin in a Dewar. That's not at room temperature. So here's carbon dioxide in its equation of state. It's a nice figure because it shows the ideal gas isotherm at 334 Kelvin, and then it shows the experimental isotherm. So here's 334 Kelvin ideal gas, and this is the experimental isotherm. So quite a bit different. Notice when you get out here, the error is not so bad. Okay? Not bad. But you get over here where you're in the condensation region, and here your pressure is predicted to be 140 bar, and the actual pressure is a little bit over 80, almost 90. So you're way off. When you're in the condensation region using an ideal gas law to predict the vapor pressure, it's going to be way off. And so these are isotherms. All of those curves are isotherms. Even this one down here is an isotherm. This is the same temperature all the way through this condensation region. Still the same temperature over here. That would be the pressure volume curve for the liquid at that temperature. So the slope here would be the compressibility, how much the pressure changes with respect to volume change at that temperature. So the isothermal compressibility would be the slope of that line. This is the this is the volume of the gas at 258 Kelvin. So that's that isotherm, 258 Kelvin. It's important that you understand all the different kinds of points that you can have on this curve. So that's a very particular point, right where condensation begins. That's the volume of the gas. And then this one over here is the volume of the liquid at that temperature. And so what would you see in a situation, let's say we have we're compressing a piston and we're shrinking the volume, and at this point we start to see drops form, liquid drops form in that piston. And here we're just decreasing the volume with that piston, and all we're seeing then is the drops are getting bigger and bigger. So it's the same pressure, we're pushing against the same pressure, but we're just forming more liquid and less vapor. So the vapor is condensing as we compress that volume in this whole region, and it's the vapor-liquid equilibrium region, VLE. And then at this point, the piston has shrunk down, and now we see no more gas phase. So the meniscus has risen all the way to the top, and now we're just pushing on the liquid. So this region to the right, at high temperature, low pressure. So look at that in this graph. I'm not drawing it up at the top of this graph. That's high pressure. I'm saying low pressure, high temperature, that's our gas domain. That's where we are in terms of gases. Large volumes, low pressures, and high temperatures. And then over here is the liquid domain. Really small volumes, low pressures, and low temperatures. And then up here, this is an important region. It's the supercritical fluid region. So we have a high pressure, very low volume, so that's the density of a liquid. But it flows like a gas. What do I mean by flow like a gas? Well, think about if we were to fill this room half filled with water. So it would be, chest deep, but all the liquid would be in the bottom of the room. It wouldn't flow to the ceiling. But in a supercritical fluid, that fluid would have the density of a liquid, but yet it would go into all the nooks and crannies like a gas. So it would flow up and around and through, holes and so on. It would flow like a gas, but it would have the density of a liquid.
That's crazy.
Yeah. And it's because we've crammed it in such a small volume, and we've heated it up so that now there's no meniscus forming. So it's a fluid. It's not a liquid or a gas. It's because it has properties of both. It has the density of a liquid, but it flows like a gas, and there's no meniscus. Okay. And so let's think about these critical constants. There's a pressure, there's a volume, and there's a temperature that's going to define that point in this phase diagram. So PC, VC, and TC, those are the critical constants, pressure, temperature, and volume, that define the critical point. You're right, I'm making a drink. So let's look at some of them. Here are the critical constants of several gases. And you can see the permanent gases, like hydrogen and helium, have really low critical constants. And so we're, look at helium, the 2 atmospheres and 5 Kelvin. So really a lot of times we just focus on the temperature and the pressure, but the volume also, the molar volume for helium would be 58 mils per mole. So we would have to, put a substantial amount of helium in there at 2 atmospheres and really cool it down to 5 Kelvin before we would, below 5 Kelvin before we could see liquid helium. Okay. Any temperature above 5 Kelvin, we're not going to get helium to condense.
Even with more pressure.
Right. Because what you do with just more pressure is you're just running it up into the supercritical fluid region. Okay. Let's look back here. So even at 5 Kelvin, ignore the temperatures on this plot, but even at, let's say we're at 6 Kelvin. So we're above this isotherm. Even at high pressure, all we're doing is just, in a small volume. We're just up here in the supercritical fluid region. So you have to get below 5 Kelvin for it to form a liquid with a meniscus. Okay. But for something like water, we need to get above 647 Kelvin to make the supercritical fluid. So at any temperature below 647, you can have liquid water. Okay, but above 647, you're not going to have liquid water. You might have supercritical fluid water if you cram it in a small volume and have a high pressure. What kind of pressure? Well, the critical pressure for water is 218 atmospheres. So that's a lot. Multiply that by 15 and you get the PSI. So quite a lot of pounds per square inch. Hexane, and so in the homework, I have you just comparing hexane and water. Just have you do a couple of comparisons between those, just to kind of get a feel for using the Clausius-Clapeyron equation, the Antoine equation, and these reduced variables to compute vapor pressure of hexane and water at room temperature. So let's talk a little bit about comparing these gases. It seems like every gas is unique. It has its own critical constants. Where do you think the differences in these gases come from? Why would they have different critical constants?
Just the amount of.
What do you think?
I think it's because of weight.
Weight?
Yeah.
Okay, so yes, they have different masses. But weight typically goes with gravity. So are there other kinds of forces other than gravity that might play a role?
Different bonding forces that can be present, like in water versus.
Okay, so the bonding forces come from, they're kind of related to weight in that you get more protons with the nuclei. And so with more protons comes what? Someone else? For a neutral species. So marching across the periodic table, we're adding protons to the elements. What else are we adding if we want to keep those elements neutral? Electrons, right? And so then that feeds into the bonding. So the bonding comes from this balance between the positive charge in the nuclei and the electron cloud. So MO theory, right? Putting essentially two electrons per bond. And so then you have, for larger elements like chlorine versus fluorine, you've got a lot bigger electron cloud. So yes, chlorine's heavier, but it also, in getting that mass in the nucleus, it also brought a lot of electrons, which makes the cloud bigger. So it's much easier to condense things that have larger clouds. Do you see that here in the critical constants? Let's just look at temperature. Look at hydrogen and helium, 5 and 33 Kelvin. And compare that to methane, 191, and water, 647. Methane, carbon's 12, 13, 14, 15, 16. So it weighs 16 grams per mole. Water, 18, not that much different. And look at the different temperatures, critical temperatures. Enormous difference. What do you see in the difference between methane and water in terms of its intermolecular attractions?
The oxygen is more electronegative. So there's just more.
Yeah. That leads to what kind of bonding? We have 3 types of interactions. We have London dispersion forces, which is just generic electron cloud motion. What are the other 2? Someone that hasn't spoken yet. Hydrogen bonding. And then what if a molecule doesn't have any hydrogen or any lone pairs of electrons? What other kinds of forces could it have? Let's say, I don't want to pick carbon monoxide because it has an oxygen. Okay, well, so carbon and nitrogen bonded together. Let's say sulfur dichloride, so SCl2. It's going to be a bent molecule. Doesn't have hydrogen bonding. Certainly got London dispersion forces because of the large electron cloud, but what else would that molecule have? Dipoles. Yeah, so what do dipoles lead to? Polar bonding. So you have polar, dispersion, and hydrogen bonding. Water has all three. But what does methane have? It just has dispersion. And methane surrounded by hydrogens, really tiny electron clouds. There's not much oscillation that can happen. So the London dispersion forces for methane are really small. Whereas water has polarity, hydrogen bonding, and like you said, the electron cloud around oxygens is pretty big and exposed. So that leads to an enormously high critical temperature for water. Remember what that indicates. That means that below that temperature you can have condensation. Okay, you have liquid water. So it will condense at temperatures below 647. And that's a function of its intermolecular attractions. If the molecules get close together, they'll stick to each other. That's what's happening this morning when you breathe out outside and your breath condenses. Those water molecules are sticking to each other as soon as they hit that cold air and forming little vapor droplets that scatter light, and you can see them. Okay. So water is very sticky to other water molecules. Let's come up with a term here that can help us understand these different attractions. And this is called the compression factor. And it's a really strange equation if you look at it, and you've grown up, as we have, with the ideal gas law. PV equals nRT, so why would you take the ratio? Right? It should be 1 all the way across. Yeah, but it isn't 1. This is a measurement of how ideal a gas is. Right? It's a great factor, this compression factor. It tells you if the gas is behaving ideally or not. So you got to just pick a volume, you put in a certain number of moles at a given temperature, and you measure the pressure. Is it the ideal pressure or not? And there's certain situations when that pressure would be lower than ideal, and other situations where that pressure would be higher than ideal. Okay. If it's lower than ideal, which is dominating, attractions or repulsions? If it's lower than the ideal gas pressure. Yeah, attractions are going to be dominant, right? Because the molecules aren't hitting the pressure gauge as hard as they would. They're attracted to the gas particles inside the volume. But if the pressure is higher than ideal, they hate each other. Let me out. Okay, they're hitting that pressure gauge and trying to get out of that container because repulsions are dominating. And there's certain regions in the volume and temperature domain where attractions would dominate and where repulsions would dominate. Picture that curve that had the attractive region and the repulsive region. And if you've got a temperature where they're hitting each other and they're really colliding hard and they're in a repulsive region, then they're going to have a higher than ideal gas pressure. And if they're hitting each other softly, interacting with the container and really almost ready to condense, then the pressure is going to be lower than ideal. There might be a temperature at which they behave ideally for a while, and then the repulsions dominate. And that would be what's called the Boyle temperature. So that was on the previous slide. These Boyle temperatures here are when that compression factor is 1 for a long period of time, and then it deviates. So if you wanted to pick a pressure where that gas behaves ideally for quite a while, then that would be the temperature that you would pick, that Boyle temperature. And so I'm kind of showing that here. This hydrogen is it looks like it's at the Boyle temperature where it's 1 for a while and then it deviates. Here's the Boyle temperature. So lower temperature, attractions dominate. Higher temperature, repulsions dominate. At the Boyle temperature, it's ideal for a while, and then it deviates. They all go up eventually. Eventually, you're at a high enough temperature and high enough pressure that their repulsions are dominant. Yes.
Why doesn't water have a Boyle temperature? Why doesn't water have a Boyle temperature?
I just didn't have it for the table. Yeah, I just didn't find it. So it's not that it doesn't exist. Yeah. So this leads to an important conclusion. So we've introduced the compression factor. Let's look now at this principle of corresponding states. And there's some homework problems associated with this, which is why I've given it a star. So since all gases have different critical points and a different compressibility factor, like it's shown in this plot here and in previous plots, okay, we can scale their temperature that they're at by their critical constants and see what happens. So we can say, let's scale water's temperature by its critical constant and hexane by its critical constant and see if that ratio matches. Okay? And so this is a reduced pressure, a reduced volume, and a reduced temperature. The values are reduced by their critical constants. Okay. Now this is the principle of corresponding states right here. The gases behave similarly when their reduced variables are used in the equation of state. So that's kind of a bold claim, and we'll see that it lines up in the next slide. This is also an engineering term where they talk about unitless pressure, unitless volume, and unitless temperature. And when I first saw those terms, after I'd graduated, I thought, what are they talking about? Unitless temperature. That doesn't make any sense at all. And so I like the phrase scaled or reduced better. In fact, I really don't like reduced. I would like scaled temperature, scaled pressure, and scaled volume because you've scaled them by their critical constants. But there's 50 different ways to say the same thing. So these are unitless pressure, temperature, and volume. And so, of course, it works best with spherical or nonpolar molecules, but it still does work with polar molecules. Look at what happened here. We've taken this plot, this compressibility factor plot, where all the different gases had different lines. And when we divide their pressure, temperature, and volume by their critical constants, they all fall on the same line. That's crazy. So this is a Z plot, a compressibility factor plot, and this is at T over Tc of 1.2. So they're 20% higher than their critical temperatures. So they're gases, okay, at 20% higher than their critical temperatures. That means nitrogen is 20% higher than nitrogen's critical temperature, and methane is 20% higher than methane's critical temperature. So every gas has been scaled by its own critical constants, and now they fall on the same line. So this is the Z plot at the critical temperature, pressure, and volume. At the critical temperature, and this is the Z plot at 20% higher, and this is the Z plot at 2 times the critical temperature. And notice how all the dots are on the same line. So nitrogen, methane, propane, and ethene. So this one has a double bond, which is different than the others. Nitrogen has a triple bond. Methane is surrounded by hydrogens. Propane is a bent molecule with CH2s and 3s. And yet they all fall on the same line. So that's pretty cool. So that's that principle of corresponding states. If you scale things by their critical temperature, pressure, and volume, they'll behave the same way in the gas phase. Here's an example of that. I'm going to leave this to you to do on the homework, okay? So you can check these math problems and understand what's going on. I do want to get to the vapor pressure questions. We're going to have a whole lab dedicated to correcting the van der Waals equation of state for condensation. That'll be after spring break. This week we're going to redo for those folks that had trouble with the bomb calorimetry. I'm going to let you have another pass at that. And so it's sort of a second week on bomb calorimetry. Okay. There's 3 forms of the van der Waals equation of state here. And what the van der Waals equation has done is corrected for the things in ideal gas law that were neglected, like the volume of the particles. And so if the volume of the room is now reduced by the volume of the particles, we need to correct for that. And so that's where this minus B term comes from. This B term corrects for the volume of the particles. And so here's the room volume, or the container volume, and we subtract the volume of the particles. Same kind of thing, only we're dealing with molar volumes here. So this is actually V over N, and you can see the N is here and the N is there. We divide the volume by N, this N's gone, that N's gone. So we have molar volume here. And then A is an attractive term, So the pressure that you would get for an ideal gas, for a non-ideal gas, that pressure would drop a little bit. And so that's due to attractions of the particles. And so that's what this A term is for. So the pressure is lower because of attractions. And then if we use the reduced variables, this is the van der Waals equation using reduced variables. And this is the one that's actually been plotted here on the right. There's a whole lab dealing with this Maxwell construction where we're trying to correct this equation for condensation. And so this would be the vapor pressure line, and these loops above and below would go away. So this is where the van der Waals equation fails, in the condensation region. Because if you think about this, this can't be realistic behavior. Because what happens is I'm decreasing the volume as I go this way, and the pressure is dropping. So I'm pushing on a piston, and then I get to a region where the piston gets pulled in. That's not realistic behavior. What is realistic is I form a liquid, and now the pressure is constant as I push until I hit the volume of the liquid, and then I really have to push hard from that point forward. So the van der Waals equation is a correction for the gas phase. It fails when you have condensation. And so the Maxwell construction, which we'll do in the lab after spring break, is where we correct that. We draw a line across the middle to where those areas are equal. And so we make a vapor pressure line. And so you'll do this in Excel with solver. You'll move that line up and down until those areas equal, and then that will be the vapor pressure for that liquid at that temperature. So let's talk about vapor pressure. There's the Clausius-Clapeyron equation, which again is shown here. You have a reference pressure and a reference temperature and the enthalpy of vaporization. You can use two pressures and two temperatures to determine the enthalpy of vaporization. Or if you have the enthalpy of vaporization, you can predict all the other temperatures and pressures. So the vapor pressure at any temperature. So if you have this and you have, say, the boiling point, you know the temperature and the pressure is 1 atmosphere for the normal boiling point, then you can predict the vapor pressure at any temperature other than that, if you know the enthalpy of vaporization. So that's a good use for the Clausius-Clapeyron equation, and that's one of the homework problems that you should work on. We do it for hexane and for water and compare the two. And so then you also have the, this is just showing different versions of that equation and some data to show that it's amazing. You have just a single reference point, and yet you can model the vapor pressure over, 300 degrees Kelvin. This is absolute pressure. This is the log of pressure. There's another equation called the Antoine equation. And this you'll find in the CRC, where you just have an A, a B, and a C constant. And so you'll see Antoine constants for gases, and that'll predict the vapor pressure, and then you have the Clausius-Clapeyron equation. So I have you do the calculations for water and hexane using both equations and with the reduced variables. So it's just 3 or 4 different calculations with hexane and water to compare the two, and using these different equations to calculate the vapor pressure. And then you'll look up literature values and see how well they did. So there's an evaluation question at the end that asks, what do you think? Which one is the most reliable? The Antoine equation, Clausius-Clapeyron equation, or using the law of corresponding states? If you know the vapor pressure of one and its critical constants, could you calculate the vapor pressure of the other one? So what I want to do is now go over the exam.